So here's another example of using one of these diagrams to figure out for a composite function. In this case, it's a composite not of two functions, but of three functions. So there's a function that takes t, and from a value of t, it produces a u and a v. So maybe that is a parametrized curve in the xy, in the uv plane, if you like. And then u and v together are used to produce three quantities, w, x, and y. So maybe that parametrized curve in the uv plane is then getting sort of twisted around in some way and being placed inside of three-dimensional space, wxy space. And then inside of that three-dimensional space, there is a scalar valued function that gives us a value of, I don't know, a temperature or something at each point in wxy space. And so it turns w, x, and y into a single output scalar called z. Right? So we feed a single number t into the beginning of this machine. That t produces both a u and a v. Those u and a v together produce a w, x, and a y. And then those w, x, and y together produce a z. And so the ultimate question is, how do I find a formula for the rate of change of z with respect to t? So if I change this t input by a little bit, how does this ultimate z output change as a proportion to the amount by which I changed the input? So see if you can use this idea of finding every pathway from input to output and using the ordinary chain rule along each of those pathways and then adding up all of those results to find a formula for the net derivative of the ultimate output with respect to the original input. One of the things that you should notice about the multivariable chain rule is that just like when we use Leibniz notation in the original chain rule in single variable calculus, you should always see that it looks almost like we could cancel out the fractions we're multiplying together to get the derivative that we're trying to arrive at. So if I'm looking for the derivative of capital T with respect to little t, as in the preview, then all of my terms, each one of the terms in my chain rule, should look like a multiplication of fractions where I could kind of cancel out, in this case cancel out the dx's, in the second case cancel out the dy's, so that I'm left with just capital T and on top and a little t on the bottom. Now, of course, we can't really treat Leibniz notation derivatives like they are fractions and cancel out like that. But it's a useful just mental check on your work to make sure that the terms that you're writing down, at least from a dimensional analysis standpoint, will have the right units. And also, because of the chain rule from calculus, ends up giving us the right thing. So anytime you write out a big chain rule expression, if you want to make sure that you're not doing something obviously bogus, just try and see if you can cancel out everything except for the ultimate output and the original input that you're trying to get a derivative from. So when we write out one of these derivatives, we'll use a partial derivative anytime that on a tree diagram, we're in a place that has more than one child, right? So this W here has a child U and a child V. That's because W is a function of several variables. It's a function of U and a function of V. So when we find the rate of change along one of those lines on the tree, that should be a partial derivative. The only time we would use an ordinary derivative is the case where we only have a single child, right? A single input to our function. So u and v here have a single input called t, and so when we find their derivatives, those are just the ordinary derivatives like we have from single variable calculus. So if we were to write out all of these different paths, let's see if I can use a copy paste to make my life a little easier. We have the first path, that's this the first branch of the tree over here. If we go to the second branch, then that is going from z through w through v through t, and so we'll just replace u here with v instead. And then our next path, our next branch, goes from z to t by way of x, followed by u, followed by t. So instead of w, we will put an x there instead. And then the x goes through u and then goes through t, so that's the third branch. And then we have a fourth branch that goes through x but goes through v after that. So we replace the w's with x's, and the u's get replaced with v's. And then the final two branches, you know where this is going, right? We end up going through y, and thence through u for the fifth branch, and through y and v for the last branch. So we get some really long, nasty looking expression. It's got 6 terms in it, and each one of those terms is comprised of 3 factors. But, you know, at the end of the day, it matches up. Oh man, it's too wide to even fit on the page. Let's see if I can shrink it. There we go. It should match up when we look at the tree diagram with all of the different ways that the input can affect the ultimate output. So yeah, it gives us a way, if we understand all of these functions in isolation, then this is how to put their derivatives together to get us a derivative of their composition.